virtual private network allows a user on a network to send and receive data across the public internet and access resources on a remote site as if they were sitting connected locally to that network. Araknis uses 3 VPN protocols: OpenVPN, IPsec gateway to gateway, and PPTP or point-to-point tunneling protocol. OpenVPN and IPsec implement security mechanisms under the VPN security model and provide the user confidentiality. Any network traffic sniffed will only result in encrypted data being seen. Authentication. Only authorized users have access to the VPN, and integrity. Messages sent over a VPN tunnel won't be tampered with in transit. OpenVPN uses 256-bit encryption through OpenSSL and uses pre-shared keys, usernames and passwords and certificates to authenticate users. OpenSSL uses an implementation of SSL, or the Secure Sockets Layer, and TLS, Transport Layer Security, which is the encryption that HTTPS uses. This is a custom protocol rather than a standard VPN protocol such as Internet Key Exchange, IPsec, or Layer 2 tunneling protocol. This is a great protocol for mobile users who work from different locations and need to connect to sites on the fly. To set up OpenVPN is really easy. We go to our router web UI and go to DDNS. DDNS is the Dynamic Domain Name System, which is much like regular DNS, which converts fully qualified domain names, or FQDN, into IP addresses. So if I type ping facebook.com, I get a response of 157.240.240.35. DNS has converted that FQDN into a dotted decimal IP address. DDNS is exactly the same and converts FQDN into dotted decimal addresses, except it has a dynamic element to it. The majority of households will have a public IP address provided by their internet service provider, and every few weeks, days or months, your public IP address may change. So if your public IP address one month is 95.223.1.45, next month it might be 5.30.244.21. You then need to update your existing VPN details or port forwarding records or anything using your public IP address with the new public IP address details, which in the end would become very monotonous. Dynamic DNS automatically updates your public IP address. Usually your DDNS address is hosted by platforms such as DinDNS or NoIP, which keeps a record of your public IP and the FQDN aliases, such as salmon.dindns.com, which resolves to 95.223.1.45. The DDNS details are set up in the case of this video on the router, which keeps communication with the DDNS platform, so when the public IP address changes, the record is updated on the DDNS platform and you don't need to worry about updating your IP record manually. So you'd be able to use salmon.dindns.com port 65000 to get to a camera, for instance, or a server of some sort, or you can use that DDNS information to create a VPN tunnel. So anyway, back to DDNS. Araknis has its own DDNS platform called Araknis DNS. So if I type in a DDNS host name and press apply, the page now shows the FQDN and the public IP address. Now I can go to Advanced and VPN and add an OpenVPN configuration. So we'll enable the configuration and give it a name. I'll call it Salmon. Under server IP, my DDNS address is automatically populated, so I'll just go ahead and press apply. Now that's done, I'll click back into the configuration and export the config file. I now put this config file on my other Windows laptop and tether my iPhone to put me on a completely different public IP address. I've saved the VPN config to Program Files, OpenVPN, and then subfolder config. In the tray, there's an OpenVPN software icon. I'll right click on that, I have the option for Salmon, and I'll go to connect. It will then initiate the connection to the DDNS server and use the certificate to authenticate the user, and then exchange keys with the server to provide an encrypted tunnel to the remote network. Now I'm authenticated and connected to the remote network. If I then go to 172.16.25.1, I can get to the router web UI and log in. If I then go to VPN, there's the OpenVPN configuration I set up in the router earlier. I can then go to another host on the network, so 172.16.25.102, and there I have a 2N IP Verso intercom. So I have access to the network no matter where I am in the world. I'll take a quick look at the configuration file. I'm not going to go into too much detail on the encryption protocols used here, only because one, that's a topic all on its own, and two, to get through that topic will take about 3 weeks. So the first line is the client, which is the VPN file. We can see the device type is TUN, which is short for tunnel, which is an alternative to TAP. Tunnel works at layer 3 of the OSI model, whereas TAP works at layer 2. Protocol is UDP, User Datagram Protocol. Remote shows the DDNS we configured along with the port number. OpenVPN works at port 1194. resolve retry -infinite. If you can't successfully create a tunnel to the remote location, OpenVPN will try the connection an infinite amount of times. No bind. The remote host isn't bound to a local IP address or port. As we keep going through, we see human readable and unreadable information on the certificates and key exchanging. In this config file, this VPN initiates the connection by using a certificate, which is issued by a CA or certificate authority. In this case, the authority is Araknis. The certificate is then hashed with SHA-1 and then signed with an RSA cipher, which stands for Rivest Shamir Edelman. We then have the public key, which is used to pair with the private key and create the encrypted tunnel and ensure the data being transmitted keeps its integrity. OpenVPN is great if you want to access your network from anywhere in the world. There's also a phone application you can download to access your network as well. A benefit to using OpenVPN, whether it's on a laptop, phone or a tablet, is you'll be able to access content which is associated to your country. So for example, in some countries your applications are limited due to location, especially when streaming video. When I was in Dubai a few years ago, I wanted to watch Sky Go, but I couldn't because I wasn't in the UK to stream. So I connected to my home VPN and then I was able to stream UK content and watch a bit of Only Fools and Horses. The next VPN protocol on the Araknis router is IPsec, which is the method of gateway-to-gateway VPN. This would be used to join two sites together to act as one network. So if there was an office in London and one in New York, the hosts could access resources on each other's network as if they were local. I've got a bit of a backstory here, so if you want to skip ahead to the configuration, then by all means please do, but what I'm doing might not make sense, so I'll quickly fire the story out. So I received a phone call and was asked to advise on configuring an open office space where business personnel can work from without the need to go to their office. The requirement was to allow up to 24 businesses to use the space and have access to an on-site printer. Each business needed separating, so there was no intercommunication between workers. The existing architecture to the network was provided by the IT company that managed the building. They provided us with a port on their mainframe switch and gave us an IP address to get out to the wide area network. So we used an Araknis AN310 router and configured the VLANs, created an ACL to allow hosts to access the common printer without enabling inter-VLAN routing. So what's this got to do with VPN? Well, we hit a snag. We found out that the firmware and hardware at the time of this video was restricted to 16 DHCP servers on the Araknis router. We created 24 DHCP servers, but when we went to assign them to a VLAN, only 16 VLANs showed. We then tried reducing the subnet size, changing the CIDR notation, using smaller DHCP scopes, but we could not get above 16 VLANs. It physically would not allow us to add any more. We then got it confirmed that the Araknis routers are limited to 16 VLANs. To cut a long story short, we tried two routers. We connected the LAN from the 310 to the WAN on a 110, configured the printer to be on a WAN port of the 310 on a static IP, which hosts behind both routers were able to access. I should also mention that the printer is wireless, so I did a lab setup, a wireless access point on a static IP using a PoE injector connected to the WAN of the 310 router and set the printer to a static address, and it connected to the wireless SSID beaconing from that access point. Anyway, without going into too much detail about the IP addressing and the architecture, this all worked and we thought happy days, this is all done. I then got a call saying that the 110 kept falling offline. Hosts were intermittently able to print, so back to the drawing board. We then asked the IT company if they could provide us with an IP address within the range of the existing one we already had. They configured their network and provided us with another IP address to configure in the WAN. So we put the printer on the management LAN of the original 310 router and had to work out how to send print jobs over the WAN. We tried port redirection using many ports such as port 9100, which is the port a lot of printers use. We could get to the web UI of the printer, but we couldn't print. We configured ACLs, disabling firewalls, but we couldn't get the printer to be discovered automatically and could only get a status of ready. So that's the backstory out of the way. So I went away and set up my lab again and thought these routers are just two LAN hosts on the IT network in the same subnet range. It's still using a provided WAN address to get out to the internet, but why not join the two networks together? My personal network architecture here is similar to the site. I have a Draytech router as my primary home router with a Cisco Catalyst 1000 8-port switch on the downlink, which then has two Araknis AN310 routers downstream. My first Araknis router is using a WAN address of 192.168.7.250, and my second Araknis router is using a WAN address of 192.168.7.85. I should say here that the Araknis 110 router is not capable at the moment of gateway-to-gateway VPN. I found this out while I was talking to the chap on site, so it was a little bit awkward. So for this demonstration, I'm sitting in Slough on the Wernham Hog network using an internal network address of 172.16.25.0/24. And I want to access the account server in Pennsylvania at the Dunder Mifflin Paper Company, but as a local user, and their network address is 192.168.1.0/24. On my Araknis router, if I go back to VPN, I have the option for IPsec, so I'll create a tunnel and name it Dunder Mifflin, and then I want to use WAN1 as the interface. Then we need to set the remote IP. This is going to be the WAN address of the remote site. So Dunder Mifflin's WAN address is 192.168.7.85. I also have the option for a DNS resolved, so I can use a dynamic DNS address, which we can find on the remote router DDNS settings page, should the site not have a static public IP address, or if you have a double NAT situation, so essentially a router behind a router, which is what I have here. But because my two routers are local, IP will work. But if you had two Araknis routers using a private IP address and need to connect across the WAN, then DNS resolve would be the best option. Under local group setup, this is the setting for the local network you're configuring the VPN from. The local security group type I'll set to IP only. I've got other options I can use to add additional authentication requirements, but I'm going to use IP for this demonstration. And now remote security group type, I have the option of IP address, subnet or IP range. I'll select subnet and input the subnet that a host on this local network can access on the remote site. So the remote IP network address is 192.168.1.0/24. So I'll be able to access resources on that IP range. So IPsec setup, this is the authentication and encryption stage to ensure the VPN tunnel is secure. The two peers, in this case the two routers, will exchange messages between one another to agree on different parameters. This stage is called the negotiation. So before I go into this, I'm only going to briefly go over what these encryption and authentication methods are. So the keying mode is the Internet Key Exchange, or IKE, with a pre-shared key. IKE is the protocol used to set up a security association in IPsec. The keying change, we have the option for V1 and V2. We are using V1, meaning that we need a symmetric authentication, so both ends of the tunnel need to have the same authentication method to work. V2 is more secure and uses asymmetric authentication, meaning that one side can use a separate key type such as RSA and the other end uses a pre-shared key. I'm just going to use the default values for this video. IPsec uses phase 1 and phase 2 to form a secure tunnel using the Diffie-Hellman key exchange. This is then used for further IKE transmissions. Diffie-Hellman establishes a shared secret between the two ends of the tunnel that further encrypt the communication. Group 1 is the default, but I have the option of Group 2 and Group 5. The higher the group number, the higher the level of encryption, but the more intensive on CPU. So let's just leave this on default for now. Phase 1 encryption is Advanced Encryption Standard 128. This is what conceals the plain text information travelling over the tunnel, so it will be encrypted by a key length of 128 bits. Of course, the higher the number, the higher the encryption. We can go up to AES 256 if we wanted to. We also have the option of triple DES and DES, or Data Encryption Standard, which is less secure than AES and encrypts 64 bits of plain text data. It's a hardly used cipher these days, so I'll just stick with AES for this video. Phase 1 authentication is set to MD5, or Message Digest Algorithm, which is a hashing function which produces a 128-bit hash, but this standard is broken and suffers from a lot of weaknesses. I have the option of SHA-1, 256, 384 and 512, which are all more secure than MD5. So I'll change to SHA-256, which in essence is SHA-2, which will be a little bit slower at calculating the hash than MD5, but will be more secure and will save on bandwidth and resources over using SHA-512. The Phase 1 SA lifetime is set to 28800, which is 8 hours. This is how long the tunnel will stay associated for until it renegotiates the new encryption key. So if Phase 1 is negotiated successfully, it moves on to Phase 2. To secure the Phase 2 negotiation, Phase 1 SA is used and the gateways agree on a Phase 2 proposal which negotiates an authentication and encryption algorithm. So we'll use Group 1 again for the Diffie-Hellman group, and AES 128 for Phase 2 encryption and SHA-256 for authentication. And the Phase 2 lifetime is 3600. This is different from Phase 1 because re-keying the IKE security association in Phase 1 uses more resources. And finally, we have a pre-shared key, which also needs to match on the remote configuration. We have some advanced options here. I'll just briefly go over them. Aggressive mode places the security association negotiation into 3 packets with all the data required for the SA passed by the initiator. The responder sends the proposal, key material and ID and authenticates the session in the next packet. The initiator replies by authenticating the session, negotiation is quicker, and the initiator and the responder ID passes in the clear. By default, IPsec uses main mode. IP compression is a low-level compression protocol for IP datagrams. It's intended to reduce the size of the data transmitted over a congested or slow network. The Authentication Header Hash Algorithm protocol provides data origin authentication, data integrity and replay protection. Each of the algorithms take a variable length input data and secret key to produce a fixed length output data. If the hashes of the 2 messages match, then it's likely that the messages are the same. NetBIOS Broadcast provides communication services on local networks. It uses NetBIOS frames that allows applications and computers on a local area network to communicate with network hardware and to transmit data across the network. Keep Alive Dead Peer Protection Interval. Keep Alive assists in keeping the tunnel alive should one end of the tunnel reboot or go down for whatever reason by sending messages at regular intervals. Should the primary WAN go down, tunnel backup will tell the second WAN to back up the connection and tell it what remote IP it needs to back up to. Split DNS requests specific domains to use the VPN tunnel DNS servers, so you could say some site.server.com should use the VPN DNS. Now if I press save and go to the other router and input the same information but on the reverse, I now have a connected status on both routers. From the Wernham Hog network in Slough, I need to access a resource on Dunder Mifflin's network, which is an account server. If I type in 192.168.1.103, I get to a basic accounts web server login page. On Wernham Hog's network is also an IP camera, which Dunder Mifflin wants to have access to. From Dunder Mifflin's network, if I type in 172.16.25.106, I get to the web UI of the camera. We've brought both these networks together so users can access resources across the WAN easily. Job done. There's now a potential security risk, so users can access all resources on both networks, which is unnecessary, as people in accounts at Wernham Hog or Dunder Mifflin do not need to access the IP camera, and users on the security team do not need to access the account server. So we just want accounts at Wernham Hog to only access the account server at Dunder Mifflin on the VPN and no other resources, and then the security team at Dunder Mifflin to access the IP camera at Wernham Hog, but no other resources. On the local network, VLANs will resolve this scenario, but what about over the VPN? Let's have a look. I've already created some VLANs on the Wernham Hog side. VLAN 1 is the default VLAN with a network address of 172.16.25.0/24. VLAN 100 is the accounts VLAN with a network address of 192.168.100.0/28. And VLAN 253 is the security VLAN with a network address of 192.168.253.0/29, which is hosting an IP camera. On the Dunder Mifflin side, VLAN 1 is a default VLAN again with a network address of 192.168.1.0/24. VLAN 101 is the accounts VLAN with a network address of 192.168.101.0/28, which is hosting the account's web server, and VLAN 254 is the security VLAN with a network address of 192.168.254.0/29. So the account server at Dunder Mifflin is now connected to a port assigned to the account's VLAN and is getting an IP address of 192.168.101.2. In the ARP table of the Wernham Hog router, the IP camera has obtained an IP address of 192.168.253.2 on the security VLAN. In Tunnel 1 on the Wernham Hog side, I'll name the connection Dunder Mifflin Account Server. On the local group, I'll change the type to range and input the IP range of the accounts LAN at Wernham Hog, which is 192.168.100.2 to 192.168.100.14. On the remote group setup, under the group type, I'll change it to a single IP address because I only want accounts to access the server on the remote network at Dunder Mifflin. I'll input 192.168.101.2. I'll leave the encryption and authentication settings as they are and press apply. Then I'll create a second tunnel for Dunder Mifflin and have access to the IP camera, but nothing else on the network. So under local group setup, group type, I'll set the IP address and put in the IP address of the camera, which is 192.168.253.2. On the remote setup, we want the hosts on the security subnet to be able to access the camera. So I'll leave it as subnet and input the network address of the security VLAN at Dunder Mifflin, which is 192.168.254.0/29. I'll change the authentication type to SHA-256 again for added security and input my pre-shared key. Over on the Dunder Mifflin network, I'll create the second tunnel and do the reverse of what was configured at Wernham Hog. We can see that both VPN tunnels are now connected, so let's test them out. On the Wernham Hog network, I'm in the 172.16.25 range. If I try to connect to the accounts server at Dunder Mifflin, the connection just hangs. If I now go to the accounts VLAN and retry the connection, it now resolves and the web page of the server at Dunder Mifflin is shown on screen. If I now connect to the security VLAN, still at Wernham Hog, I get an IP address of 192.168.253 and now try to connect to the server. The connection again just then hangs. If I now go over to Dunder Mifflin's network, if I connect my Windows laptop to the security VLAN and do an IP config, I've been given the IP address of 192.168.254.2. On the web browser, if I go to 192.168.253.2, I can get to the web UI of the camera and go ahead and log in. Then finally, to show that I only have access to the camera from Dunder Mifflin's network, on the Wernham Hog network I have an IP intercom which I accessed earlier, which is in the default VLAN at the address of 172.16.25.102. If I attempt to connect to it from Dunder Mifflin's network, the connection just hangs. If I now go back to the Wernham Hog network, I'm back on the default VLAN. If I go to the same IP address, I'm welcomed with the login screen of the intercom. You'll need to be careful when setting up an IPsec gateway to gateway VPN. If you have two networks with the same private addressing infrastructure, you'll start running into issues such as IP conflicts or accessing the wrong resources on the remote network because they have the same host value of the IP address. PPTP, or point-to-point tunneling protocol, is an older VPN tunneling method that's pretty much obsolete. As a VPN protocol, it doesn't require authentication or encryption, therefore it's not very secure. It's just an option on routers if security is non-essential. For the time it takes to configure PPTP, you might as well use OpenVPN, which implements authentication and higher levels of encryption to protect the information that traverses the tunnel.